Alright, the purpose of this lesson is to introduce you to how to calculate beta naught and beta 1. So this is the data set that we've been practicing with since we pretty much got into the correlation section. What I've provided for you are the 5 columns of data that are associated with calculating R. So you can see X, sum of X is equal to 25, X bar is 5. You can see column for the Y variable. Sum of Y is 45, Y bar is 9. And then the next 2 columns says take each of those raw scores and square them. So 9 squared is 81, 13 squared is 169. At the bottom you see that I have summed them up for you. So the sum of X squared is 165, sum of Y squared is 445. And then our cross product column, the cross product for person number 1 is 9 times 13, which is 117. And again, I have summed that column up for you. So there's really nothing new on this top part. And as it really turns out, there's not really anything new on the whole page. We're just going to be using some of our old friends in a different way, I would say. So let's take a look at how do you calculate beta naught, beta 1. And as it turns out, we're going to calculate beta 1 first. And you can see the formula there. I want you to take a moment before I tell you, but I want you to stop and think about where you have seen that numerator before and where you have seen the denominator before, because you have seen each of those in a previous lesson. And I'll slowly work my way up to the board and write this on the board for you. But hopefully you're noticing that the top part of this formula is the sums of squares between X and Y, which is the numerator in our calculation formula for R, or a computational formula for R. So that is a number you should have already calculated. And then we're going to divide that by, take a look at that, the bottom part of the formula, and hopefully you recognize it as the sums of squares and X. So once you have calculated these 5 columns at the top, you pretty much have everything that you need to do to do most of the math for correlation. So beta 1 is equal to the sums of squares between X and Y divided by the sums of squares in X. So I went ahead and plugged and chugged the numbers into the formula for you. In the future, if you're doing this and you don't want to go back and recalculate 253 minus 25 times 45 divided by 5, all of that divided by 165 minus 25 squared divided by 5, you can go back and find 28 is the numerator in our calculation formula or computational formula for R, and the sums of squares in X was 40. And so beta 1 in this problem is 28 divided by 40, which is 0.7. Now, strangely, that actually also is our R. But that is just coincidence. So that is not something that is normal. You should expect it to happen. But with this particular set of practice data, it is something that did happen. All right, so we've got the 5 columns at the top. We can plug and chug the numbers to find beta 1. And then nextly, we need to calculate beta naught. Beta naught, again, is our y-intercept and is equal to y bar minus beta 1 times x bar. So because we need beta 1 to calculate beta naught, we need to calculate beta 1 first. And so again, I've plugged the numbers in for you. 9, all right, so beta naught is equal to 9 minus 0.7 times 5. 9 minus 3.5 gives us a slope of 5.5. And so we can now write our more specific prediction equation. Kind of in my vernacular, I refer to this just kind of as the regression equation. But once we get specific beta naughts and beta ones in there, I kind of tend to start calling it my prediction equation, because we're really ready to predict some scores. So you see the prediction equation written there. Y prime is equal to 5.5 plus 0.7 times x. And so then what I did for you is gave you a couple of x's to plug in. Just practice using that formula. So the first one, if x is equal to 5, what is y prime? So 5.5 plus 0.7 times 5, so you just plug that 5 in for the x, gives you a y prime of 9. I guess I should write that on here for you. Equals y prime. And then if x is equal to 9, 5.5 plus 0.7 times 9 is equal to 11.8. And so again, there is our y prime. One of the things that I do want to point out to you is that prediction equations tend to be only good for any x that is within the range of your x values of your observed scores. So here are our observed x values, and so notice I actually used two of the observed scores for you to practice with. So when x is equal to 5, we would have predicted a y prime of 9, and notice here someone actually scored a 7. For x is equal to 9, we predicted 11.8, and notice that someone actually scored a 13. So again, we know that our prediction is not perfect, and we're going to get into it in our next lesson about how do you calculate the standard error of prediction, because we want to answer how good are these predictions. But back to the point I was making, if someone came in and scored an x of 12, you could probably go in and put their score into our prediction equation. I don't know how much faith you would put in your predicted score, because 12 was not within the range of our observed scores that we were using when we created this prediction equation. So something to kind of think about when you do your homework. You're going to create a prediction equation, and I'm going to have you calculate a couple of predicted scores, and what you'll notice is the x values that I give you are within the range of the observed values that were used when you were creating the prediction equation. All right, so there's how you calculate beta naught, beta 1. Again, I would say the good news is once you've done a lot of the work to calculate R, the correlation coefficient, you are good to go in terms of having most of the information you need for these calculations.